Okay, good morning everybody and welcome to the MaREI Retrofitting Homes Symposium. My name is Jamie Goggins and I'm going to chair the symposium today. So we're delighted with the interest in the event. We have over 500 people that register for the event, and we can see that people are still logging in at the moment. However, we've a packed schedule, so we'll get started with the symposium, which is scheduled to run for about 2 hours or 2 hours and 15 minutes. So two fantastic producers there in the background, Tara and Aoife, who are helping us with the technology. Put a huge effort in today, so thanks to them very much. So I'll give a quick introduction to MaREI. So MaREI is the SFI Centre for Energy, Climate and Marine, working across 13 academic institutions in Ireland with its headquarters in UCC. This morning you will hear from researchers based in Cork, so in UCC and CIT, in Dublin, TU Dublin and ESRI, and the National University of Ireland in Galway, where I'm based. We also have speakers from the Irish Green Building Council who are working closely with us. So this morning we'll be using Slido to gather your questions and some for interaction in there. So if I can please everyone go to slido.com on your phone or your computer and use MaREI as a hashtag to bring you to the event. So I can see great, there's a lot of people on there already. There's a couple of questions up there already in it. So we'll pose the questions to the speakers at the end of each of the sessions. So as you can read the questions yourselves, and you can like them, and as they get liked, they get moved up close to the top. So as to test Slido, so this is the first question. So if you go onto slido.com and into the poll there, we've asked everyone where you're joining from today. So we can see already we've 47 people answering that, all the way from Galway. Don't understand that one in the middle, somewhere in Cork, Dublin, and so on. That's great. That's it. So it's so if you go onto your phone, slido.com, and that's where we can get there. Okay, so if we just move on to the next slide. So just a little bit of background to set the context, I suppose. So we have approximately 2 million homes in Ireland, of which 1.7 million are occupied. About 9 out of 10 of those homes. About 9 out of 10 of those homes are single family dwellings in there. So detached, semi-detached and terrace houses, where 11% are from apartments in there. On the top right hand side there, you see that about 36% of those are owner occupied without a loan or mortgage, with a similar number that are owner occupied with a loan or mortgage. Then we have 18% that are rented from the private landlord, and about 9% between rented from a local authority or a voluntary organisation. On the bottom right there, we have the year of construction for the homes, with the colour code the same as the colour code in the pie chart on the left hand side in there. So we can see that our building stock come from, right across the different periods, which the highest rate in growth in the 90s and the early 2000s. So what's the quality of that building stock like? So we'll just move on to the next slide. And again, so the quality in terms of its energy performance is determined by the energy performance certificate. So this is a requirement from the EU that all buildings have an energy performance certificate. So that energy performance certificate in Ireland is called the Building Energy Rating in there. So it's so all new homes that are built since 2019 or November 2019, and all those that get significant retrofit have to be an A2 building energy rating or better. So to put that in context, the building regulation 2005, or if you build a house to the regulation 2005, the new regulations has a requirement to have a energy performance that is about, in energy consumption, primary energy consumption, that's about 30% of that from the reference building in the 2005 regulations. And the emissions associated with the house, about 35% of that from the reference building of the 2005 regulations. On the right hand side, that's the, so each of these building energy ratings, or the BERs, have to go into the national database. It's hosted by SEAI, so there's over 9,000 entries to date, and you can see the different quality of buildings, I suppose, in terms of the building energy rating that we have, with the average BER being a D2. So, Kira in her first presentation is going to delve into that database in a bit more detail. So so as I said, the average BER is more than is a D1. Last year, the government published a climate action plan, which has a target to retrofit 500,000 homes by 2030. So that's on average 50,000 homes per year. So that means retrofitting to a B2 standard or better, because that is the current requirements. So to put that in context, I suppose since 2013 or so, there's about 23,000 homes per annum that have been retrofitted. But of those last year, 2,600 were retrofitted to a B2 standard, and that was actually the highest amount that went to a B2 standard. So that shows you the kind of ambition, I suppose, from the Irish government. So we'll go on to our next question then in Slido. So if you could go on to slido.com, and then our next question. There you go. So next question, the Irish government's Climate Action Plan 2019 set a target for 500,000 homes. That's 50,000 homes per annum on average, receiving a retrofit to B2 or better. So what I want to know is that number, 50,000 homes per annum, is that equivalent to all the occupied homes in Cork, in Galway, in Castlebar, or in Dublin? That's great. So we can see people voting away there, and that's great. So just as we're a little bit tight on time, so I'll talk through the different ones. So the top vote there is Cork at the moment. So Cork has actually about 50,000 homes sorry, Cork. Yeah, so Cork City is about 50,000 occupied homes. So that's the answer to that one. So effectively, that that the ambition from the Irish government is to retrofit all of the homes that are occupied in Cork City in a given year. So that would be, say, this year or next year. In Castlebar, well, it's actually the whole of Mayo would be equivalent. If you retrofitted all the occupied homes in Mayo, that's 50,000 homes. In Galway, we have about 30,000 homes. So you need Galway City, all of the homes retrofitted in a given year, plus another 20,000 homes as well. Dublin City is about 220,000 homes. So it would take about 4 years at the rate of 50,000 units per year to retrofit all of the homes in Dublin. So if we move on to the next poll. So the next poll then is, let's put it into context in terms of the costs. So the overall sum of 35 billion that's required. So sorry, SEAI estimate that 35 billion is going to be required to make all the building stock low carbon by 2050. So what I want to know, is that equivalent to the cost of the post-2008 bailout of the banks, the estimated government borrowings for the COVID-19 pandemic, the construction sector GDP in Ireland, or the overall GDP in Ireland? That's great. So just for those of you to be able to go into these polls, you need to go into slido.com and click on the polls, and you can try and answer the questions there. You can also pose your questions and answers to the speakers for later on. That's great. So yeah, so the Irish government, so the top voted one there is the expected borrowing for the Irish, for the COVID pandemic in Ireland. So that's well, the numbers are changing every day, but John Fitzgerald last year in his Irish Times article estimated about 30 billion. So we're in a sort of similar region. The bailout of the Irish banks in 2008, was 64 billion, so that's almost twice the amount. So 64 billion with a net cost of the bailout of banks of 42 billion. Ireland's GDP is about 10 times the 35 billion, so I think it's about 340 billion or so. And the construction sector GDP is about 8.8 billion in 2019. So I know it's a lot of money that's required to be retrofitting our homes to make them. But I do believe that it's a major economic and employment opportunity for the country, investing in people in Ireland, especially in the construction sector, to improve the quality of our homes. So since people spend typically 90% of their time indoors, having safe, comfortable, healthy and energy efficient homes is of interest to most. Okay, so just two more polls to do just to get some feedback from yourselves. So what's the biggest barrier to deep retrofit in Ireland to scale? So that ambition of 50,000 homes per annum. What do people think is the biggest barrier? So you can just type in your answers in there into Slido. It should have popped up on your phone or on your computer in Slido. Okay, so it's a word cloud, obviously. So the more people that put in the similar word, the larger the word gets on the screen. Very good. So you see the cost here is a huge thing. So cost is about, to do a deep retrofit, is about between 25,000 and 75,000 per annum to do a deep retrofit of a house. MaREI later on is going to go through some more detail of that from the super home scheme that Tipperary Energy Agency administer in terms of what the costs are in there. The SEAI in the pilot scheme for the deep retrofitted, out of the 325 houses that were done that went from an average of an F to an A3, the average cost was 54,000 euros. So that gives you the kind of idea in there. So we definitely need our financial institutions, government support, and private individuals to invest in this. So that's fantastic. 115 responses there. You see cost, money, finance are the big ones. Interesting. SEAI. Josephine might be interested in that later on. So if we could just move on to the last poll, and then I'll hand over to the main presenters. So it's an interesting time, I suppose, in Ireland at the moment in terms of there's government formation talks that are coming close to an end. So what should the next government do to help achieve the ambition for deep retrofitting of 50,000 homes per annum? So if you're advising the government in there, what should they do to help to achieve the ambition? So again, I suppose the finance side comes through here big time in these responses so far. Grants, funding, and then that long-term commitment to funding. I think that is hugely important at the moment. That's the uncertainty there. So those that are involved in retrofitting at the moment can't scale up because of the uncertainty of whether there's going to be a market in terms of the grants and the commitment from the government and so on in there, and the financial institutions. But very good. Some policy regulation in there, stimulate the labour market and so on. Okay, great. So if we just move on to the next slide, thank you. Okay, so we have this morning we've 12 speakers coming up. So we have 2 sessions in there. So there's 6 speakers first, and that's going to be moderated by Josephine Maguire, who's the National Coordinator for Sustainable Energy Authority of Ireland. So Josephine has been more than 10 years leading strategy and programs related to retrofitting homes in SEAI. And then after those session, then we'll have an afternoon session with another 6 speakers and facilitate discussions. Unfortunately, Brian Norton from TU Dublin wasn't able to join through as a facilitator this morning, so I will do that. So I'm going to hand over to Josephine for the first session.
Great, thanks very much, Jamie. You're having fun there. So great to be here, everybody. We have a great lineup for you this morning. Lots of interesting speakers talking about very interesting things that we all need to do over the next 2 years. We're tight enough on time, so I'm going to move quickly and just introduce our first speaker. It's Dr. Ciara Hearn. She's Head of Building Engineering in TU Dublin. She's been studying and analysing the Irish housing stock for more than 10 years, and particularly is interested in looking at how we integrate heat pumps into thermally refurbished stock. So Ciara, over to you.
Thanks, Josephine. And thanks, Jamie. Good morning, all. I'm here this morning to present research that was published in an Energy and Buildings paper in 2019. And the data source for the research is the EPC, the Irish EPC or BER database, which was downloaded in July 2014. And the analysis is on pre-2006 dwellings. On the next slide, you will see the number of state refurbishment grants paid in Ireland by 2015. And you'll see the lion's share of grants being paid to what are perhaps the less disruptive measures such as roof and cavity wall insulation. And on the next slide, you'll see that the level of thermal refurbishments are leading to a bimodal distribution of the housing stock. On the left-hand side of the graph there, you see Mode 1 dwellings. Mode 1 dwellings represent thermally retrofitted building elements, where Mode 2 are as-built dwelling elements. And Mode 1 presents a more pronounced profile than that of Mode 2, as thermal retrofits are able to achieve more harmonised levels of insulation. And as more retrofits are carried out, building elements are migrating from Mode 2 as built into Mode 1 thermally retrofitted. And this is lessening the correlation between a dwelling's age and its energy efficiency. In the tail of the distribution, you'll notice a statistically anomalous spike highlighted in blue there. This spike is seen consistently across all periods of construction across walls and roofs, and it relates to default U value selection by the assessor. On the next slide, you'll see that default U values are selected by the assessor when information on the building fabric is lacking. And this is so as to avoid costly and disruptive investigation measures into the fabric. They're standardised to support the reproducibility and robustness of the EPC as an asset rating or as a comparative tool. The defaults are necessarily designed to be normally pessimistic, and this is to avoid offering a better than merited energy rating, but also to encourage the homeowner to maintain records and the assessor to seek out records that might improve the energy rating of the dwelling. However, research in 2006 has found that the defaults in use currently bear no relation to the statistical distribution and are in fact punitive. A quarter of walls in the database are characterised by defaults, and this over-reliance on, combined with the punitive nature of defaults, leads to the data presenting an overly pessimistic view of the stock, and it constitutes a structural error in the data. On the next slide, you'll see that we thus clean the default U values from the data before fitting a bimodal curve. And fitting of the curve allowed us to establish the percentage of thermally retrofitted dwellings and the percentage of as-built dwellings, along with the mean and standard deviation of each of the modes. And on the next slide, you'll see the results. And the results are characterised for pre-thermoregulation and post-regulation dwellings. Now, pre-thermoregulation dwellings are assumed to have been constructed initially without any insulation present, and they're ascribed default U values 2.1 watts per metre squared for walls and 2.3 watts per metre squared for roofs. It can be seen there from the results that 50% of pre-thermoregulation walls and roofs have very significant levels of insulation, and this is really positive. Post-thermoregulation dwellings are assumed to have insulation levels in line with the prevailing building regulations of the time, and you'll see the table there below showing the building regulations prevailing at each period of thermoregulation. This research is on pre-2006 dwellings, and interesting, you can see from the results a significant level of energy upgrades in post-regulation dwellings, with circa 70% of walls, we'll go back there if you don't mind, 70% of walls and 84% of roofs insulated to better the U values prescribed in the 2006 regulations. Now, it's estimated at the time that 25% of the dwellings within the database are there because they were grant aided. So this level of thermal retrofits is attributed to both grants, but also autonomous energy upgrades, or perhaps the building or the dwellings were constructed to better the prevailing building regulations of the time. So on the next slide, we'll see the results from 2014 compared with that of 2001. And we can see that 58% of walls were insulated to a U value of 0.66. So this is a mean average across both pre and post regulation across the stock. 67% of roofs to U based, and 53% of floors are insulated to a U value of 0.5. So on this, go ahead, Aoife. On the last slide, we see Ireland compared to other Northern European countries, such as the Netherlands in green and Sweden in blue there, as well as Poland in purple. Now, there's a prevailing sentiment in the literature that Ireland has one of the worst thermally performing building stocks in Northern Europe. However, due to thermal upgrades, both autonomous and grant aided, we would contend that the long held view that the majority of Irish dwellings are thermally substandard is no longer valid. Thank you.
Brilliant. Thank you very much, Ciara. Perfectly on time. You must have really timed that earlier.
I did, otherwise I would have been ahead of it.
Well done. Okay, thanks so much for that, Ciara. Lots to think about and sort of good news for us, which is brilliant. We're going to move on next to Dr. Gianluca Grilli. Gianluca is a research officer in Energy and Environment Group of the ESRI. His interests include economic aspects of energy and natural resource management and non-market valuation and econometric modelling. He's going to talk to us about retrofitting residential properties and fuel choice in that move. Gianluca, over to you.
Thank you, Josephine, for introducing me. So yes, I'm Gianluca Grilli from the Economic and Social Research Institute, and I'm presenting this work, which is a joint work with my co-author John Curtis, and it's about retrofitting residential properties and fuel choice. So next slide, please. So this work has been funded by Gas Network Ireland within the MaREI framework, and we are really grateful for the funding. Next slide. So basically the idea is that fuel choices here are mostly related to adoption of natural gas in residential properties. And this is because natural gas is a policy relevant fuel in terms of achieving the targets of emission reduction by 80% in 2050. So although natural gas is not really renewable, it's still less polluting compared to other fuels, for example, oil, peat, or coal. So it's relevant from a policy perspective to try encouraging a wider use of gas in residential properties. And since there is an evidence that properties are more likely to be refurbished when people move to a new property, so when a household buy a new property, probably they will consider at that time to refurbish the property rather than when household live in the same property for a while. So we try to have a look at the household decisions of refurbishment with gas between 2011 and 2016. So we took a look at the properties that were not fueled with gas in 2011, and we've seen what are the factors, what are the households that changed the fuel in 2016. We have these 2 years because there are the 2 years where we have census data available. And next slide, please. So this is still work in progress, so I will just present a bit some results to show you a bit of the flavor of what we've been doing. And basically, a first interesting result is that when people buy a new property and move to the new property, these guys are 6% more likely to consider gas as a refurbishment option compared to people who remained at least in the same buildings. And then we also seen that there are good few determinants of refurbishment choices, and in particular for gas, an important variable that household seems to consider is the distance from the gas network. Because when a property is further away from the gas, so the more distant is a building from the gas, and the less likely people are to be connected, because distance affects the cost of connection. So the more distant you are from the gas, network, and the less likely you are to be connected. Another interesting result so far is that the previous fuel affected the choice. So if you take as a reference the buildings that were fueled with electricity in 2011, you can see that buildings that were fueled with oil were 25% less likely to be connected to gas than in 2016. And buildings that were fueled with peat or coal as primary energy fuel were 11% less likely to be connected in 2016. And this is probably because electricity is more costly for the final users compared to oil, peat, or coal, and gas is cheaper compared to electricity, but it's not really cheaper compared to oil, peat, or coal. So probably people would consider the cost of fuel when they evaluate switching. And this is understandable, but from an environmental perspective, probably this is not really desirable because oil, peat, and coal are polluting. Electricity still is polluting, but you can always convert the production into renewables, whereas oil, the others are non-renewable, so there's very little to do. We also detected an association of the social class. There are some differences across the social class, so managers, professionals, and unskilled workers are more likely to be connected compared to manual workers. And in the next slide, you will see that there are some other factors affecting these fuel choices, which is, for example, the number of rooms, which is a proxy for the size of the house. So larger houses are more likely to be connected in 2016. The house type, so detached houses and semi-detached houses are more likely to be connected compared to terraced houses and flats. Larger households are more likely to be connected compared to smaller households. So probably these decisions are affected by the cost as you would normally expect from fuel choices. So these are the results that I have to present today, and thank you. Still work in progress, as I said.
That's brilliant, Gianluca. Thanks so much for that. Again, very interesting stuff to think about. Jamie asked me to remind people just of two things. One, we're recording the session here today, so that will be available later. And the other thing is just don't forget we have Slido there, and please submit any questions you have through slido.com, #MaREI. Okay, so listen, we'll move on quickly to the next person. It's Thomas McGeer. Thomas is a PhD researcher at UCC. He's focusing on energy efficiency pathways across various sectors of Ireland's economy. And this work involves the construction of sector-specific emissions models for Ireland using the LEAP tool. Thomas, over to you.
Hi, Josephine. Thanks, Emil. Great to be here this morning. Thanks everyone who's tuning in. So I'm going to take my own advice from the title here and respect the importance of timing and get straight in because I only have 6 minutes. So I'll jump into my first slide, please. So a quick overview of what we're going to touch on today. I'd like to, I suppose, present and highlight the LEAP Ireland 2050 model, which was used to investigate these different diffusion pathways. This piece of analysis looks at the importance of pathways, so comparing implementation pathways instead of looking at just point-in-time targets. So that's the difference of what is the effect of, I guess, annual retrofit targets across different archetype dwellings, and what does that mean in terms of early action, delayed action. So what we've done is we've looked at the Climate Action Plan target of 500,000 dwelling retrofits, including 400,000 heat pumps, and then a quick spoiler. So this is basically the results straight off the bat. Early action delivers an additional 0.82 million tonnes of CO2 equivalent in the early action scenario relative to the delayed. So we'll have some time then for some conclusions and policy implications. Can move on there. So a quick overview of the method. So identifying targets is obviously the initial focus of this piece of work. So 500,000 dwellings, 400,000 retrofits. Sample diffusion rates are used, so that's the BAS model formula using, as I mentioned, sample P and Q, which represent innovation and imitation coefficients within that equation. This provides us with annual pathways or annual retrofit amounts, which deliver which are different but and distinct, but deliver the same end year target in 2030. We used the LEAP Ireland 2050 model to then actually simulate those pathways and do some scenario analysis. So again, the scenarios being early and delayed action based on those diffusion rates, and then implicitly that generates these carbon budgets for the period 2020 to 2030. So moving on. Quick background on context, you've heard some of this already, I suppose, but large-scale deep retrofitting has been slow and challenging in Ireland. The SEAI deep retrofit programme, I think it was 325 deep retrofits delivered for the period 2017 to 2019. So there may have been some autonomous ones, but in terms of ramping that up into a national scale and delivering these 50,000 per annum retrofits, that's going to be challenging. There's about 23,000 shallow retrofits completed per annum to varying levels of energy efficiency based on which combination of retrofits. And I've noted a paper here, publication, that indicates that the current retrofit choices are in fact suboptimal and could be improved. So moving on. So the assumptions within the paper, you see on the top here, the early action target compliance scenario and the delayed action target compliant scenario. You can see the number of dwelling retrofits for terraced and detached homes and how many of them include heat pumps. So WHP is with heat pump for each of the years 2020 to 2030. It's worth noting here that this analysis can, I suppose, give the impression that the target is very achievable because we have nice simple curves. But if you look at this space between 2019 and 2020, you'll see that there's a large scale increase in both the early and delayed action scenarios that's required to deliver these. So, and again, we're interested in the difference between them. I'll just note really quickly that the archetype dwellings that we have within the LEAP Ireland 2050 model, there's 9 archetypes. That's apartment, terrace, detached. And then within them, we have different BER categories of, or groups of A, B, C, D, and E, F, G. So moving on. This slide shows some of those initial results and the difference between the two scenarios. What we're really interested in, I suppose, is the difference between those two dashed lines. So if we look at the solid green line up top, that's the number of retrofits per annum in the early action scenario. So we're ramping up to approximately 30,000 per annum in this year in 2020, and then we're tapering out to maybe 60,000 in 2030. And then the dashed green line below is the equivalent greenhouse gas emissions reduction associated with that scenario. Equally, the red solid line is the annual retrofits required within the delayed action scenario. So there's still, I mean, it's ambitious, but still 20,000 per annum in 2020, but rising up to 72,000. And the difference between those two scenarios, I have the figures here on the right in terms of the actual, the numbers in terms of the reduction in both scenarios. But that's the difference between the two dashed lines is that 0.82 million tonnes that I mentioned at the start. And yeah, just to mention, both of these scenarios are cap compliant, so 500,000 retrofits. Moving on, sorry. 1 minute, that's perfect. So, I mean, conclusions from this, clearly early action is required to deliver those maximum benefits, but I think more importantly, it really highlights the need to start focusing on target delivery pathways and not get bedded down in these point in time targets for 2030. It's really important to be able to visualize and indicate how many retrofits we need in each year, not alone just for compliance, but also checking in on ourselves every year or two to see how well we're doing. Early action can deliver some additional benefits, i.e. less pressure on the transitional pathway. So I indicated there 16% less retrofits in 2030. That's 72,000 retrofits in the delayed action scenario versus 60,000 in the early action scenario. So it makes it a little bit easier later on. And that further analysis is required to quantify the impact of the pre-works condition of these dwellings in terms of scenarios that we might develop, because I've assumed an even distribution across CD and EFG, detached and terrace dwellings. So we could look at that in more detail in terms of, you know, focusing just on the worst performing or the least energy efficient dwellings going forward. So thank you very much.
Brilliant, that's great, thanks so much. Just a reminder, everybody, again, Slido's there. Any questions you have, any commentary on what you're seeing up here that you'd like to get a bit more information, do let us know. So next up we have Orla McGinley. Orla is doing a PhD at NUI Galway on retrofitting of existing buildings to reduce energy consumption while also improving comfort, health and well-being. Her research areas include quantifying and demonstrating wider benefits of energy efficiency retrofitting of existing dwellings, and she's also looking and involved with us and looking at the place of the one-stop shop on this. Orla, over to you.
Yes, so thank you for the introduction there, Josephine. So today I'm going to be presenting research entitled Beyond Energy Efficiency, a deeper insight into the multiple benefits of retrofitting homes under the SEAI's Better Energy Community Scheme. So we'll just move on to the first slide. So research has clearly demonstrated that the energy efficiency benefits of retrofitting existing homes. However, retrofitting has multiple benefits within an economic, environmental and social context. So this might include the likes of increased property value or energy cost savings from an economic perspective, energy consumption or emissions reductions from an environmental perspective, and the likes of improved comfort, improved health, improved well-being, improved occupant satisfaction, or fuel poverty alleviations, for example, from a social perspective. So it is crucial that these wider benefits are quantified and demonstrated to relevant stakeholders in order to drive retrofit uptake, retrofit investment and policy design. And retrofit and policy design should also aim to maximise some combination of these benefits. So in addition, using quality case study data to demonstrate these benefits is deemed central to creating an evidence base of the multiple benefits of retrofitting. And this is deemed crucial to de-risking the retrofit decision-making process for homeowners. So just moving on to my next slide. So in recognition of the need to demonstrate these wider retrofitting benefits, this study defined a set of economic, environmental and social key performance indicators for residential retrofits from a householder perspective, and determined the economic, environmental and social benefit which was attained through retrofitting based on a pre and post retrofit performance assessment of these key performance indicators using case study data which was obtained from 5 case study dwellings shown A to E in the diagram there, which were located in the west of Ireland, and these dwellings were retrofitted under the SEAI's Better Energy Community Scheme. So as can be seen from the diagram there, the economic KPIs that were assessed included the life cycle cost and payback period. The environmental KPIs that were assessed included the annual energy consumption and emissions reductions associated with the works, and the social KPIs that were assessed included comfort improvements, fuel poverty alleviations and householder satisfaction. So moving on to the next slide. So just some of the results. So the economic assessment revealed that 3 out of 5 case studies, namely A, B and D there from the diagram, achieved life cycle cost reductions post-retrofit as a result of the post-retrofit operational energy cost savings. In terms of the payback, these case studies also achieved payback within 30 years for the works. So for example, as indicated there for case study dwelling A, they achieved the payback within 10 years. However, 2 out of 5 case studies assessed, so namely C and E, did not achieve any economic benefit in this regard due to increased energy consumption post-retrofit. So moving on. So in terms of the environmental benefit, 3 out of 5 case studies, so namely A, B and D, as you can see from the diagram, achieved post-retrofit reductions in energy consumption and emissions of up to 60%. One case study, namely case study E in the graph there, did not achieve any environmental benefit post-retrofit as a result of increased electricity consumption. And case study C seen no change. So moving on. So in terms of the social benefits that were received, the assessment of comfort, this was based on temperature and relative humidity sensor data and householder survey responses. And this revealed that 3 out of 5 case studies achieved post-retrofit temperature improvements with an average temperature increase of about 1.1 to just above 3 degrees recorded. The percentage of readings in these the percentage of temperature readings, recorded in these dwellings that were to be recorded to be below 18 degrees also decreased post-retrofit in these case studies. And so in terms of relative humidity readings, one case study, so namely case study dwelling A, you can see a sample of the results shown, noted some improvement in terms of the relative humidity in the dwelling post-retrofit. In this case study, the percentage of readings that were recorded to be above the upper recommended limit of 60% relative humidity decreased post-retrofit. However, in 3 out of 5 case studies that were assessed, over 50% of the post-retrofit relative humidity readings taken remained above this upper recommended limit of 60% relative humidity. So the householder survey results differed slightly from the measure results. and they showed that 4 out of 5 case studies actually cited that they were more comfortable post-retrofit, despite the fact that the measured data in one of these case studies did not necessarily reflect theoretically more comfortable conditions. So in terms of the fuel poverty alleviations, there were no fuel poverty alleviations achieved in the dwellings post-retrofit, nor under the future period that we assessed in the study. So just moving on. So finally, the householder satisfaction was assessed in terms of the householder satisfaction with the overall retrofit process, the works quality, the technologies that were implemented, the engagement of contractors, and the perceived benefits from the householders of the works. So we have some direct quotes there from the householders shown. So some key satisfactions cited by the householders were generally related to improvements of the quality of life and comfort within the home post-retrofit. While some of the major dissatisfactions included dissatisfaction with technology, so that might be in terms of how the technology was going to pay back, or just having some negativity as to the new technology, for example, preferring their older heating controls. And other dissatisfactions included the lack of information that was given in terms of how to operate and maintain the technologies that were installed. So just moving on. So the main conclusions from this study were that economic, social and environmental benefits are achievable through retrofitting projects, that various levels of retrofit benefit were achieved across the case study dwellings that were assessed, and that no two dwellings actually received the same level of benefit or combination of benefits. So thank you very much for your attention.
Great, thanks very much for that, Orla. Lots of interesting stuff there, and I'll certainly be interested to find out later on about the buildings that didn't receive a benefit after the upgrade, that economically they were higher use. So I'm wondering if that was changed circumstances, but we'll get to that in the Slidos, I'm sure, later on. Okay, so we'll move on now to Dr. Maria Lopez Zambrano. Maria is a postdoc researcher in the MaREI Centre in NUI Galway and a certified passive house designer. She's looking at examining the effectiveness of innovative building structural elements and systems, and in retrofitting existing buildings to achieve NZEB. So Maria, over to you. Maria, are you with us? You might need to turn on your you're a little it's quite hard to hear you, Maria.
Oh, you can hear me now?
Yes, that's better. Thank you.
Okay, thank you. Thank you so much. Well, let's get started with the next slide, please. Okay, why today I'm going to talk about data collection and analysis. Well, in Ireland we have around 2 million dwellings and only 1% of NZEB. So if the trend is that in the future achieve the NZEB level in the majority of them, it seems very obvious that we need to retrofit our existing stock. So why is important data collection and better insights into deep retrofit programs? Well, because with this, we can know how the stock dwelling is, the energy saves, the cost of the measures, and to identify the main barriers. And with all this information, we can answer. It is possible to achieve the NZEB level. It is affordable for the owner and for the country. If our current retrofitting schemes enough, or it is necessary to use them, and what are the most successful measures. So, next, please. To do that, arise a collaboration between the industry and academy, in this case, Tipperary Energy Agency and the NUIG. And the project is in the frame of the SFI Industry Fellowship. And this project has different sub-projects, but one of them is super data, with the aim to identify the key points to achieve the NZEB level, and in this case, to help super home program. Next, please. What is Super Homes? Super Homes is a one-stop shop for energy retrofit created by Tipperary Energy Agency. And in 2015, Tipperary Energy Agency launched a pilot program with 10 houses with the aim to achieve the NZEB level. And almost 2 years later, EEI introduced the deep retrofit pilot scheme. And so with the support of these grants, more than 200 houses were retrofitted by super homes. Next. So what we are going to do that? Well, creating a huge database, including three important pieces of information. The cost of the works, the BER pre and post retrofit. And to have an idea of the scale of this database, 325 dwellings in total were retrofit by SAI deep retrofit. Temporary Energy Agency retrofit 219 between super homes and other deep retrofit programs. And the date of super data contains 98 dwellings, so that have full information, ABA rated, and the data is confirmed in the three sources that we use. Next, please. So coming back to the aim of the project to identify the key points to achieve the ANSAP level from A3 to A2, the database tells us that the 65% of the houses were A3. A mean of 333 euros per square meter were spent to pass from the original stage mean A2 to A3. And in the case of the ANSAP, the percentage was 35, and the mean 418 euros per square meter to pass from the original state to the ANSAP. So if we analyze the whole budget, the cost breakdown in 4 categories, we have the building envelope including ventilation and air thickness. To pass to A3 to ANSAP, we need to invest at 33% more. In the space, water and heating, around 5% more, in lighting 14% more, and in PV panels 67% more. So if we pass to the next, please. If we analyze the envelope in detail, we can see that the main difference is in the walls, following for the floors. But by contrast, in the windows and doors are very, very similar. So in summary, the key points to upgrade from A3 to ANSAP, according with the data that we have in this database, is that we need to increase the total budget in 82 euros per square meter, spend the 77% of this extra money in the envelope, of course improve the walls, and install a PV panel, because 91% of the ANSAP dwellings have one. So ending with the actual data, we can understand better the typical costs of deep retrofitting homes through the Super Homes program. Now we are analyzing if it could have been economically feasible to achieve the new ANSAP standards for all homes in the Super Homes program rather than the A3 rating. And the project is running until September, so we expect to have a full report of the findings completed by then. So thank you so much for listening and enjoy the symposium.
Brilliant. Thank you very much, Maria. That's great. Again, lots of interesting stuff there. We're going to move soon on to Dr. Philip Marchand. Philip will be the last speaker. So if you have questions, please put them in Slido, because when Philip finishes, we will then move on to the questions in Slido. We will look to answer a number of them. Obviously, we're short on time, but we will take all questions that are put into Slido, get whoever they're directed at to answer them, and we will circulate that afterwards. So Dr. Philip Marchand, Philip is a research fellow in the Dublin Energy Lab in TU Dublin. His PhD was on adaptive building facades. He currently participates in the Horizon 2020 Drive Zero project, which is aimed to accelerate the sustainable and cost-efficient renovation of buildings with a user-centered focus. So Philip, over to you.
Thank you very much, Josephine, for the introduction. First, I'd like to also thank you for this opportunity to present some of the findings and methods we're undergoing in our Drive Zero project. Please, could you move on to the next slide? Wonderful. So Drive Zero aims to drive a decarbonization of the European building stock and to accelerate deep renovation processes. And we want to do that with a consumer-centered and locally based circular renovation approaches. Ultimately, this project aims to make deep renovation more environmental friendly and more attractive for consumers and investors. One of our objectives is to develop easy to install plug and play prefabricated solutions for elements of the building envelope and for building services. To develop and implement a circular deep renovation solution, we are using actually 3 strategies that are first to reuse and recycle locally available materials by urban mining, use renewable environmentally friendly materials, and use bio-based materials. Next slide, please. So for our case study, we're working with Dublin City Council, and we aim to retrofit 2 or 3 semi-detached terrace houses. Those are built in the 60s, and the main issue we're addressing here are the poor energy performance. With a building energy rating of grade F, and that's resulting in poor health and comfort, but also we have a poor accessibility to the space for disabled and elderly people. So some of our objectives here for our prefabricated facade are to bring actually the BER to an NZEP standard with a 2 rating, develop an easily integrable solution that is scalable to the building stock, develop attractive consumer-centered business models, demonstrate cost efficiency across the whole value chain, which requires a volumetric addition actually that is shown here in this picture. And we need to go through all these steps with a user-centered mindset where, for example, occupants engage in the design process, they suffer minimum disruption during the integration. We want to repurpose the space efficiently and increase access to elderly people and disabled people. Next slide, please. To meet with this objective previously discussed, so we developed this monitoring action plan. Our concept included the use of IoT ICT-based solution with various levels of information according to the targeted end users. We also aim to design a future-proof solution that would be a smart building with customizable, modular, and expandable monitoring and control solution with potential connectivities to services. And we wanted to dynamically inform and communicate with end users. And this is not only to provide information to the occupants, but also for the occupants to provide feedback during the building operation. And in our methodology, we consequently had to identify attractive and understandable user information. With that process, we define mandatory and voluntary monitoring parameters to quantitatively and qualitatively evaluate the building performance and the benefits to the occupants. With that in mind, one of the challenges in the selection of monitoring equipment that we had was obviously to find a trade-off between the cost of equipment versus the benefit. Next slide, please. So what are the type of data we need to monitor? Those were classified among the 7 pillars of sustainability. The mandatory parameters that must be monitored are the delivered energy demand and the renewable energy produced and consumed. In the health and well-being category, that would be air temperature, relative humidity, and CO2 concentration, as well as qualitative and perceived information of well-being. And then with circular behavior, we want to engage with occupants and communities to find new consumers patterns and figure out the general value for human activities beyond just financial. So for the purpose of our case study, we will also cover water and material aspects that are voluntary actions. Next slide, please. With those monitoring parameters in mind, we developed this monitoring architecture representing the many sensors located in the various rooms of our case study and their connectivities to loggers, mostly via wireless M-bus. The idea behind the many energy monitoring sensors is to disaggregate as much as possible energy generation and consumption. With such architecture, we will be able to quantify the energy produced and consumed from photovoltaic, the performance of a heat pump, and the energy demands for space heating, ventilation, domestic hot water, lighting, and appliances. For communication reliability and avoid using actually the Wi-Fi network of the occupants, data will be communicated to a server via GPRS. The information collected can then be displayed to the occupants via a home monitoring screen or through a mobile application. Similarly, the occupants will be able to provide a live feedback about perceptive health and comfort parameters for the screen and the app. And finally, all data will be curated and analyzed to demonstrate the improvement of the building performances and validate a business model. Next slide, please. And finally, I want to thank you, and I welcome you to visit our website and contact me should you have any further questions. Thank you.
Great, thanks so much for that, Philippe. Again, really interesting stuff there. So brilliant. We have lots and lots of questions. So if that's okay, I'm actually going to go to you first, Kira. Do your results suggest we have much less CO2 emission saving potential from retrofitting than previously would have been estimated?
Yeah, definitely. A lot of our reporting from the housing stock has been based on defaults, modelling the thermal consumption or the energy consumption of the dwelling stock based on defaults. And it does lead to an overestimation of the potential savings. Certainly, we see that there's energy efficiency intervention. So the sort of the low cost or the least destructive measures have been somewhat availed of. We need to get deeper, perhaps into floor insulation and dry lining and external insulation to see results. The other issue we have is that we are not an apartment dwelling nation. We're a single family house dwelling nation predominantly. We have the fourth largest proportion of single family dwellings across Europe, and that surface area against that volume means we have high heat losses when compared to apartments. And also we have the fourth largest floor area in Europe. So what's happening is our energy upgrades are being surpassed by ever growing larger homes. So yes, in short is the answer.
Okay, so the next one I'm going to ask, I see there's a number of questions coming in on using gas in homes. So one talks about, is that really going towards NZEB, or maybe we're talking biogas? How will it help meet 2030, 2050 targets on reduction of fossil fuels?
Well, so gas is certainly not the ultimate solution to all our problems. This is clear. But the thing is that at the moment, natural gas is much less polluting compared to other fuels, and so it's a ready-to-use solution that we have for reducing at least the emissions. So having a wider use of gas will surely reduce the total amount of emission. And since this anonymous question cited biogas, actually biogas can only be used with the same pipelines of the natural gas. So in the medium to long run, there might be a switch from natural gas to biogas. And if pipelines are ready, if people are already connected to the network, then it's much easier to switch to biogas. At the moment, I think that it's not really cost effective to use biogas, so it's there should be solutions to make biogas cheaper. But once these methodologies will be available, probably having biogas will be much faster. And of course, in the very, very long run, probably natural gas would not be the ultimate solution, but still at the moment it's one of the main solutions probably to reduce fast the emissions. So this is basically the idea. Okay,
great. Thank you very much for that. Orla, we might just move to you next, because I was interested in this, and I see a number of people on Slido are also interested. Out of the 5 case studies, there was a couple who had increased energy use, one definitely. And just I'm wondering if there was some change in circumstances, or they didn't understand the technology, or did you get in under the hood there to figure out what was the situation?
Well, so in terms of the study, we didn't get we could only allude to possible reasons that we thought this might have occurred. So in one of the case studies, their energy consumption increased post-retrofit. However, there was no real indication whether they didn't know how to use the technologies, or some of the possibilities that you mentioned there. But what we might assume in that particular case study was that they took back their benefit in terms of comfort, because there was a notable comfort improvement in this particular dwelling. So whether or not that was a take back there is something that we could allude to. And then in the other dwelling that I mentioned that seen an increase in energy expenditure, so it wasn't so much that their energy consumption increased after the retrofit, it was that they moved to an all-electric heating system after the retrofit, so therefore their electricity consumption increased. And looking at the relative price of electricity to other fuel sources, that was the reason for the increased energy expenditure in that dwelling. So I hope that's clear. Yeah.
Yeah, no, that's great. Yeah, obviously more work to be done there, and possibly bigger samples and all sorts of things, which we all need to work together on. I'm going to go for the next one because lots of people really like it. Why isn't sheep's wool, which is an environmentally sustainable solution to insulation, utilised more across the Irish construction sector? I think I might know the answer to that, but I'm going to pass over to the experts. Who would like to answer? Nobody?
Philippe is trying to answer. Unmute yourself, Philippe.
Yes, sorry about that. Yeah, so one of the aspects that we are bringing forward also in our project here, we will definitely have a strong focus on natural and actually bio-based material. And so that is certainly one of the components that we will look at. So there is a huge impact there, and urban mining is possible, but somehow difficult. So hence the bio-based and natural solution here.
Great, thank you very much. I'm going to put one in myself here. I just wonder, Ciara, on the heat pump side of things and the increase in electricity, is there a connection there? And then do you find that other usages go down?
Yeah, sorry, Josephine, I don't know the answer. What I was looking for, would heat pumps retrofit into existing radiator systems when the building fabric was insulated? And I found that they can be a direct retrofit to boilers, because the radiators are now oversized for what is the load, and you can avail of the low surface temperatures. So I found they can be a plug and play into existing heating systems, but I haven't looked at the electricity side. I was looking at the thermal side.
That's fine. That's fine. So listen, last one. The last one is for Tomas. How big a jump is it in reality to get from where we are to the starting point for your retrofit pathways?
Okay, thanks, Brian. I mean, I guess we can't underestimate the scale of the challenge in actually delivering that. It's highlighted in a couple of those figures where you can see the jump in 2019 to 2020 in terms of both the early and the delayed action scenarios. So I mean, I suppose, yeah, to answer the question, it's unprecedented and very challenging. I mean, reaching an average of 50,000 per annum hasn't been done before in Ireland, deep retrofits, and it's going to be very costly. But I mean, there's more work to be done in terms of analysing the feasibility of that target, which is why I think it's important to start the discussion and start focusing on pathways rather than point-in-time targets. So not being too hung up on the 2030 target of 500,000, but understand how do we rapidly increase the number of retrofits as soon as possible, regardless of how many that is.
Yeah, that sounds like good advice. Okay, listen, that's great, guys. Thanks so much for that session. And like I say, we'll look at all the questions and try and get our speakers to answer them. And Tara's going to do something magic to get that all out to everybody, as well as the recording will be available. I'm going to hand back now to Jamie to start the next session.
Thanks, Josephine. Thanks for doing a fantastic job. So that's the first session finished. So we're on to the second session now, and we have 6 speakers. I suppose just before I introduce them, that last question about one of the questions there about the sheep's wool, just to put it in context, we do a good bit of research on this in terms of the embodied energy and carbon associated with the materials that we use. So to put it into context, if we're going to have a new semi-residential building to the NZEB standard, that the materials technologies for that building, they could account for about 45% of the life cycle energy. Could potentially be all of the global warming potential, so all the greenhouse gas emissions could be associated with the materials if we use fully renewable in the operation of our buildings, and potentially about 55-60% of the life cycle cost. So we really do need to think about the materials that we put in, and using an indigenous bio-based material such as sheep's wool would be welcomed. And obviously with the market the way it is for sheep's wool in there, we need another alternative market for it. So I think it would be great if people could pursue that and get it through so it could be used as a product. So into the second session then. So second session, as I said, we have 6 speakers. First speaker is Dr. Gary Goggins, who's a research fellow in UIGO, and he's going to talk about socio-technical changes and sustainable lifestyles. So over to you, Gary.
Perfect. Thanks, Jamie. Yeah, so I just want to maybe think about retrofitting as not just a way to introduce sustainable technologies, but also as a way of introducing sustainable lifestyles and what might be the opportunities there. And as Jamie said, this means thinking of retrofitting in terms of socio-technical issue and not just a technical issue. So I have 3 points that I want to make in the presentation on the next slide. Very quickly, I'll go through the first 2, which is first that we need to understand how we understand the problem of unsustainable energy use or excess energy use has great implications for the type of solutions that we come up with, or the type of solutions that we even try to come up with. So I'll look at some work we've done on that, then also provide a brief overview of the limitations of some of the more common approaches, and explore the potential for incorporating a practice-based approach, drawing on lessons from a Horizon 2020 project that's just finished called Energize. So on my next slide, you'll see a problem framing typology that we developed. So what we've done is we've looked at over 1,000 initiatives that seek to reduce energy use in households. And these initiatives all have some active involvement of households. So they see households as active consumers rather than just passive recipients. So despite looking for this active household angle, we still found that changes in technology and products and changes in individual behavior were dominant approaches. And we would say that these are more simplistic approaches, and they don't take into consideration the need for systemic changes in production and consumption systems, which it's increasingly obvious that we need if we're going to achieve our climate targets. So over 75% of initiatives looked at these changes in technologies, which is efficiency or else decarbonization of supply generally, and changes in individual behavior, which are usually based around providing more information for consumers, or else behavioral economics approaches that try to nudge consumers in the right direction, etc. So my next slide, I'll just quickly look at some limitations of these approaches. So efficiency approaches, well, some of the main problems are that the focus is always on the energy input rather than the energy service. So we don't look at the meanings or the levels of service, levels of comfort, convenience, mobility, etc. that's expected or that becomes normalized. That's also a relative rather than absolute focus, and standardized norms such as heating whole homes instead of single rooms, and normalization of bigger, better, bigger houses, as Kira says, etc., reduces efficiency gains. There's also an abstraction of the social cultural context, so we don't take everyday life seriously and the kind of nuances in it, and often we expect rational behavior, which is never the case. Individualistic approaches also fail to deliver long-term change. They require considerable effort. The results are often very modest, and there's often a high level of rebound, such as people increasing their comfort rather than reducing their overall energy. And finally, the focus is generally on isolated behaviors rather than a systemic approach. So I'm looking at an alternative option, which my next slide looks at how we might understand energy use through a practice-based approach. So here we shift the focus from individual behaviors to look at the social organization and what underpins energy use. Here we understand energy use as a consequence of everyday practices. So we look at the service, what energy is used for mobility, heating, cleaning, cooking, etc. And we say that these are socially significant, and people are carriers of these practices. We reproduce things in certain ways. So if we can understand why people do this, then we can understand opportunities for change. My next slide just shows the different elements in practices. When we look at from a practice theory approach, we say that there's three different key areas: materials, conditions, technologies, meanings and social norms, and competence and skills. So practice-based approach will try to change these elements, so either recraft by changing individual elements, or else substitute practices by completely changing all one for the other, like swapping driving for cycling, for example. We can also look at how practices interlock, so how maybe mobility relates to your work, or how eating relates to shopping, relates to mobility, etc. On the next slide, I'll just give you some results that we had from Energize, where we used a practice-based approach. So we went to use a living lab. We went into people's homes to ask them to try out new ways of living, and we asked them to reduce their maximum indoor temperature to 18 degrees. So we wanted to learn, experiment. We didn't to tell them what to do. We wanted to maybe see how they cope with doing this. And so the living lab was really a intervention, and we observed how change came about. So on the next slide, I'll just show you some of the results that we got. This was across 8 different countries and over 300 households. So we found that people could quite easily reduce their indoor temperature by at least 1 degree without compromising any level of comfort. They didn't really notice. Also, the ideal temperature doesn't exist. It depends on the room. People like it warmer in some rooms, cooler in others. Life stage, elderly people tend to like it warmer. Social relations, people would turn on the heat if guests were coming over. They were afraid of looking bad in front of other people having a cold house. Also, we found people's bodies are excellent sensors. They were very adaptable. People found it cold at the beginning, but as the challenge went on over the 4 weeks, people were able to adapt, and they said, oh, I got used to it being cooler. They also intensified practices, wear warmer clothes instead of heating the whole house, and lower heating in the bedroom was desirable. So they didn't want the bedroom to be as warm as the rest of the house. So taking these lessons on the next slide then, and how can we use these findings in retrofitting? Well, instead of living labs being a rupture in habits and routines, maybe we can look at retrofitting as a rupture in habits and routines. And say, well, while people are getting retrofitting done, there is some upheaval in their lives, and can we now introduce new, more sustainable practices? Can we challenge social norms around unsustainable behaviours? And if we can do this, and we can, I believe, well, who should take responsibility? Who needs to be involved, and in what capacity should they be involved? Apologies for going over. That was a quick 6 minutes, but thank you for listening.
Thanks, Gary. Okay, so yeah, just to remind people that it is people that we are dealing with. It's we as engineers we might focus on technology and so on, but behaviour is hugely important in the success of any project that we are going to use technology on. So next presenter is Paul Moran. So Paul Moran is a postdoc researcher in UI Galway, and he's going to delve into DEEP, which is the process or the procedure methodology that we have to use in Ireland to get the building energy ratings, so to see if it is a good predictor of energy demand and indoor temperature. So over to you, Paul.
Thank you, Jamie, and hello everyone. Thanks for attending my presentation today, where I plan on showing you the findings from some of my research, which has examined the difference between the theoretical and actual energy consumption and indoor temperatures of homes before and after retrofit. So what is DEEP? For those who are unaware, DEEP is the Dwelling Energy Assessment Procedure for assessing the energy performance levels of residential buildings in Ireland, and it also produces their energy performance certificate, which we have discussed in previous presentations today. So what are energy performance certificates used for? So as I've illustrated on the next slide, energy performance certificates are seen as a tool for providing clear and reliable information to homeowners and tenants to assess and compare their energy performance levels, encourage homeowners to invest in measures to improve the energy efficiency of their home, and to assist governments in forming policies to achieve energy reduction targets and energy performance levels within the building sector. However, these energy performance certificates are produced in Ireland and Europe using standard steady state formulae or quasi steady state formulae, And research studies have found that these formulae can be inaccurate when estimating the savings that retrofits can produce in buildings. So some of the research studies that I've examined have found energy saving deficits to range from 2% all the way up to 98%. So what's driving these energy performance targets to be missed? So as I've illustrated on the next slide, some of the reasons associated for these differences is the assumptions that we use regarding the performance of the building fabric, and then the different assumptions we assume regarding the building characteristics, and then assumptions we assume regarding the energy consuming behaviors of the people in those buildings. So I've listed some of the factors that I found from my research there, and then as part of my research I examined the energy consumption, indoor temperature of homes before and after retrofit in a housing estate in Dublin. So I've illustrated these on the next slide. So the housing estate itself was constructed in 1994 and 2000, and it consisted of mid-terraced, end-terraced and semi-detached homes. The monitoring was for 6 months pre-retrofit and up to 18 months in some case studies post-retrofit. The houses themselves received a standard retrofit package with cavity wall insulation, attic insulation, new windows, new doors, and an upgraded heating system consisting of a gas boiler and hot water tank. So these houses were monitored. So 22 of these houses were monitored in depth. So their electricity and gas demand was monitored. Up to 4 rooms in each of the case studies had temperature and relative humidity sensors installed in them. And then we interviewed householders in each of those case studies. So gas was the primary source of energy for the space and water heating in these buildings. And as I've illustrated on the next slide, the theoretical and actual energy demand of those buildings, both pre and post retrofit. So the results I show here are for 3 months of the year, so March, April and May. So on the left hand side, I've shown the pre-retrofit demand, and on the right, the post-retrofit demand. So the red line I've shown on each graph illustrates where the data point should lie if both the theoretical and actual energy demand is in agreement. However, as we can see, pre-retrofit deep overestimates the energy demand of those homes. And for many of those houses, in a large way, only one house actually uses more energy than deep actually predicted. So while the energy performance gap actually reduces post-retrofit, the initial pre-retrofit estimation means that only 25% of the expected energy savings were achieved. Now, looking at those data points, one might suspect that deep also overestimated the indoor temperature levels of the homes, but as I've shown on the next slide, deep actually underestimated the indoor temperature levels of those homes. So for deep, when deep estimates the energy demand of a home in terms of its space heating, it is based on the floor area of the building, the efficiency of the heating system, the temperature differential between the indoor and outdoor, and the indoor gains that the house experienced from solar energy gains, and then the gains from the appliances themselves, but then also the heat loss coefficient. So the heat loss coefficient is the U value performance of the building elements, the area of the building elements, and then the air tightness of the buildings themselves. So because deep overestimated the energy demand and then underestimated the indoor temperature, we suspect that the heat loss coefficient was initially overestimated because the U values for the windows and doors pre-retrofit were based on default U values because we didn't have any other information. Then for the floors, pre and post retrofit, we also had to use default information, and then we had to use default information for the air tightness of those buildings. So if we want to rely on if homeowners, tenants, governments want to rely on the information that these tools provide in terms of the energy performance levels and indoor temperatures of these homes, we need to be able to verify that the values that we input into those tools are actually accurate. Now, we weren't able to estimate how much the heat loss coefficient possibly was driving the difference in energy performance levels, and the sample size in Australia was of course small. So we need to be able to have much larger studies examining exactly what are the factors driving the energy performance gaps between these kind of tools and what actually happens inside those buildings. So finally, just to reiterate some of my points, deep overestimated the energy demand of these houses and underestimated the indoor temperature levels. only 25% of the actual savings were achieved by these buildings, and that the heat loss coefficient is expected to play some sort of part in that. And as I said, further studies is needed to exactly determine what is causing these kind of energy performance gaps between the theoretical and actual. Thank you. If anybody has any questions, you can email me directly or pop them in the slido there, and I'll answer them afterwards. Thank you.
Thanks, Paul. So our next presentation is by Marta, Dr. Marta Fonte, who's going to talk to us about indoor radon levels within buildings. So we have to understand the air quality as well as energy and so on. So we've seen a whole range of presentations today talking about more than just energy savings. That's important. So over to you, Marta.
Thank you, Jamie. Thank you to all the attendees today in the symposium. So I'm going to talk about the impact of retrofitting on indoor radon levels. If I can see, yeah, there it is. So yes, I'll introduce in the first slide for those of you who are not familiar with radon. Radon is a radioactive gas generated as a decay product of radium in the decay series of uranium-238, which is present in the Earth crust, providing a continuous source of radon from the ground. So radon is considered the second leading cause of lung cancer after smoking. As I mentioned, it comes from the ground, and in the outdoor environment is not a health issue, but if it gets accumulated inside buildings, it can derive in a high radioactive dose when inhaled, and inhaling radon has been shown to cause lung cancer. So to regulate indoor radon exposure, a reference level was defined. There is the latest European BSS directives says that recommends a reference levels for radon in dwellings shall not exceed 300 becquerels per cubic meters. And in Ireland, we have set a reference level of 200 becquerels per cubic meter in dwellings. Radon can enter a building or a house in different ways. We can see in the picture on the left-hand side, in the right-hand side, the different key ingress routes of radon. The dominant mechanism of radon entry into buildings is pressure-driven airflow, and there are different factors affecting radon entry in the buildings, such as ground potential, building characteristics, and ventilation. This is very important when we talk about energy efficient buildings. How are the building characteristics and the building envelope? We'll see in the next slide what are the radon mitigation and remediation techniques. There can be categorized in three. First, barriers by sealing soil gas routes or installing radon members before the concrete slab. The extraction by extracting by soil depressurization system or pressurization, and the ventilation, both natural and forced. The main or the most effective radon mitigation technique is soil depressurization system. We see the central picture on this slide is a soil depressurization system, which is characterized by a suction point, a exhausting pipe, and then a means of extraction, which can be a mechanical structure or a passive structure. So what we do here with this technique is we create a depression below the concrete slab. So we attract all the radon below the slab, and we exhaust this outside the building, preventing his entry. So it is important for the soil depressurization system to be very effective. What's the building envelope? What are the characteristics of the aggregate layer and the pressure field extension? Moving on to the next slide, and relating to the retrofitting measures and the energy efficiency buildings, these are characterized by high air tightness, mechanical ventilation, and high quality insulation. In general, we should get a lower indoor radon concentration due to these factors, because when we have a better building envelope, we can prevent radon entry, and if we have appropriate control ventilation systems, we can evacuate pollutants, in this case radon and other pollutants as CO2, when they enter the building. So by looking at the recent publications on the radon impact related to the energy efficient buildings, we see a table here. We have two examples of publication, and if we move on to the next slide, we have a few more. I'll highlight here on the second row, there is a study conducted in France, 2016, with more than 3,000 single houses, trying to monitor the influence of thermal retrofit and building characteristics on indoor radon. The reported effectiveness of this study was an average of 155 becquerels per cubic meter radon indoor concentration, which is below the reference level, but it was found that the thermal retrofitting increased in a 21% the indoor radon concentrations. If we go on to the fourth row, we have a study conducted in Ireland with 89 houses in passive and new build energy, zero energy buildings. In general, lower radon levels were found, but in some cases it was high radon levels were reported. And I highlight in the last row a study conducted last year in Germany, also comparing refurbished houses with non-refurbished in around 100 buildings. A wider distribution of indoor radon concentration was found, but the average indoor radon concentration nearly doubled for energy retrofit buildings. All of this leads to the last slide, in which we had also the quotes from some experts of the European Radon Association, stating that on average radon concentration are much smaller in new arted buildings, which means when we have refurbished houses, we should have lower radon concentration. If the air exchange, the mechanical ventilation systems are well calibrated, the high radon concentration are rather unlikely. But the measure of the air tightness and the mechanical ventilation alone might not be sufficient. So energy efficient houses do not guarantee low radon levels. And this will be the conclusion that we cannot forget radon when we are refurbishing houses. So we should also take into consideration the measures and how this affect the air quality and radon within. And that's all. Thank you for your attention and attending this symposium. If you have any questions, you can pop them in Slido and I'll be answering afterwards. Thank you.
Thank you very much, Martha. That's great. So we're going to move over now into, I suppose, more the technology focus side of things with the next two presentations. So our next presenter is Noel O'Neill, who's a chartered engineer and also lectures at TU Dublin. He's going to talk about adaptive facade. So over to you, Noel.
Thank you, Jamie. Good morning, all. So today I'm going to be describing my PhD project, where I look at the potential for use of multifunctional facade systems for net zero energy buildings. So on the first slide there, I'm going to outline the project. So the project is to design and characterize a full scale solar thermal test cell for the collection and storage of solar thermal energy using what is a novel multifunctional facade system. On the left hand side there, it shows a kind of an isometric schematic of the cell itself, and on the right hand side you can see a cross section through the cell, or through the cell that's in the middle of being built. On the outside facade, outside element of the facade is a kind of vacuum glazing, and then you have an air gap, a controlled air gap with a use of fans. It can be passive or forced, and then on the inside is a switchable suspended particle device, switchable glazing. So this energy will be collected in the gap and used in a future thermal store. Okay, so on the next slide, the aim of the project is to design the solar thermal cell with a multifunctional facade to collect solar thermal energy, and then to measure it and test the performance of the multifunctional facade, operated under various different typical scenarios, and I'll look at some of them, and that would be expected. Okay, and finally to test the methods to analyze it and test the performance of it. So the next slide for a look at where the cell is located. The cell is located there, is shown on the right-hand or top left-hand side of your screen in the Grange Gorman campus. It's basically a porta cabin. The picture there is kind of an old picture. It's been upgraded since then. It's split into kind of three rooms. On the far left-hand room is the cell itself. It's been thermally upgraded. It's south-facing facade, and the multifunctional facade is fitted on the outside of the cell. The cell in itself is approximately 2.8 meters long by 2.5 meters wide and 2.5 meters high. So how it's going to be operated is shown on the next slide. So it's operated kind of initially 4 modes. We're looking at the operational concept is for 4 typical modes. Firstly is the mode 1 on the top left-hand corner. It's the heating mode. It's when heating is required. The vacuum glazing provides a thermal insulation, and the solar thermal energy is transmitted through the suspended particle device in the transparent mode. Mode 2 then is the top right-hand mode. Its heating isn't required. The dampers are arranged as 4 dampers, top and low-level dampers are arranged to direct energy to the store, to the phase change material store, and it's collected up there for use at a further time. The mode 3, then the bottom left, is the suspended particle device or transparent glazing is in the opaque form, and the energy, the air is heated and it's transferred into the store. And then finally, mode 4 is the bottom right-hand shading and ventilation. Here we use the store is fully charged, and we can then use the ventilated facade to kind of help ventilate the area, and also if you don't need heating, also shade it. Okay, the components of the facade itself. Okay, the first components, the first slide there shows the dampers, high and low level dampers. External part of the facade, as I said, is a vacuum glazed panel. There's a gap of around 300 millimeters between the panel and between the 2 panels, and the internal panel is a switchable glaze panel, a controlled switchable glaze from opaque to transparent. In the facade itself, you can see there's kind of small fans. They're just typical computer fans. There's about 7 of them. That's the components. Then click on for the actual measurement devices. So we're going to be measuring inlet and outlet temperatures, air speed or air mass flow rate, and external air temperature and external solar radiance levels. Okay, so they're the kind of main temperature readings and main data we'll be recording. So next slide for the initial operation. So the initial operation is what we're going to call it external air heating, where the air comes in the damper A1, shown as damper A1 on the bottom left-hand corner of the facade. The fans are switched on, so the 7 fans will be on. They can be operated from 1 to 7 in lots of different modes as well. So the fan will be switched on, it'll blow air up into the out-through air damper number A4, and the transparent glazing will be, the switchable glazing will be in opaque mode. So it'll collect, it'll heat the side of the switchable glazing, and air will be heated up and then transferred into the space. Next mode then is the internal heating. It's very similar, it's basically the same, except it's going to be the damper A3 is open. Then finally onto the methodology and testing end. So we're going to look here, we're going to use the Hotel-Wheeler Bliss. It's basically a solar air thermal collector, and we'll be measuring the solar energy collected as a ratio of solar energy that hits it based on the area of the collector. And then finally, the potential energy can be measured if we move on to the next slide. The potential energy will be measured based on solar load ratio. Okay, so we're looking at the solar heating factor. So solar load measures will look at the solar heating factor as amount of energy that is provided by the solar collector based on the energy required for the room. If the full heating is provided by the solar collector, you don't need any heating, so it's 1 or 100% or 1. Anything above 1 is potential for solar energy to be collected. Again, I'm going to be looking at all of these on the various different operational scenarios. So that's it. Thank you very much. And if you have any questions, I'll gladly take them. Thank you.
Thanks, Noel. Very good. So we move on to our next presentation. So another one on technology. So this is being given by Adam O'Donovan, who's a postdoc researcher in CIT, and he's going to concentrate on domestic air source heat pumps. So over to you, Adam.
Thank you, Jamie, Tara, Aoife, and all those at MaREI who made this event possible. I would also like to take the opportunity to thank all of those who contribute to the work I'm presenting today, which is about some ongoing research in relation to the in-use performance of different energy efficient technologies. And in this case, I'm focusing on domestic air source heat pumps. So next slide, please. So figure 1 shows the number of installed heat pumps in European countries as 2017 for the European Heat Pump Association. And we like heat pumps because they have a very high efficiency value, upwards of 300%. Heat pump systems, air source inclusive, have been seen as the heating systems of the future. Naturally, this has led to an increase in market growth, with the European Heat Pump Association reporting 5 years of consecutive growth up to 2017. Given this demand and increase in market growth, it is important to know how energy efficient air source heat pumps are in reality. Today, I would like to share some ongoing work from the Design for IU project focused on the in-use performance of air source heat pumps. I'll go through some of the targets and projections, some of the performance metrics that are used, and then try and compare manufacturer performance, performance in the BER database, as well as some values from in-use field studies. Next slide, please. So there is an ambitious expectation that there will be over 600,000 heat pump installations in residential buildings by 2030. Here's the cumulative figure in 2017. In figure 2, you can see it. And over the next 10 years, we're likely to see upwards of 50,000 heat pumps installed annually. That's what we want. While this is ambitious, and the cumulative target here is obviously very low at the moment, there is some cause for hope. In figure 3 on the right, we can see the number of buildings in the BER database with heating system main efficiencies greater than 100% and less than 100%. And for those of you who were religiously following the BER database like me, 2019 marked a very interesting year, where this was the first year where heating systems with efficiencies greater than 100% outnumbered those with efficiencies less than 100%. So this reflects the increase perhaps in heat pump technologies over boilers. However, given the heavy investment in a single technology and the scale of installation ambitions, it's crucial that we understand the performance of heat pumps. Next slide, please. So the performance of air source heat pumps are typically represented by instantaneous values like this coefficient of performance, or can be represented by manufacturers seasonally using a seasonal coefficient of performance, which, if you look at the green box, takes into account various factors, various variables. SCOP is typically calculated and reported by manufacturers for typical climates, the average colder or warmer climates. And as you can see in figure 4 here, we have the binned number of temperatures for these climates, but also for Dublin. In Ireland, efficiency values that are entered into deep account for climatic conditions in Dublin. So in theory, SCOPs in Ireland should be higher, or calculated SCOPs. Next slide. Table 1 indicates the performance here of 9 heat pumps from 5 manufacturers in Ireland. We took into account various heat loss indicators to give ourselves a range of rated capacities. And overall, you can see there's a minimum of range from 3.2 to 5.2, with an average of 4.4 for space heating, and a range of 2 to 2.9, and with an average of 2.5 for domestic hot water. There is some variance between manufacturers of around 200%, and this is usually due to the quoted source temperature for space heating, where we're looking at radiators or underfloor. Next slide. Figure 5 here shows box plots of the performance from the BER database and compares this to the manufacturer line in white. Where we compare the manufacturer's quoted values, you can see that the mean values and the median values from the BER database for the manufacturer and BER seem to be quite close. However, there is some difference, about 40% difference between manufacturer values in the BER database. On the next slide, you will see a table of 9 field studies of actual performance from Europe. And a lot of these studies have a mixture of heating and hot water, and it's difficult to extract exactly heating from hot water, but overall, the seasonal performance factor identified in these studies ranges from 1.2 to 4.5, with an average of 2.8. In blue, I've highlighted a study from the UK, one of the largest studies, which has a similar spread to the overall table here, and has an average season performance factor of 2.7. So the question here is, do heat pumps perform as they should? And our manufacturer values, BER values, are they all matching up? So on the next slide, you'll see a comparison of all three, where we have the range of values entered into deep, we have the manufacturer values in white, and we have the average from that in-use study in the UK in red. And what we can see here, what is clear, is that the performance gap does exist. This can be upwards of 150%, depending on how we examine it. And for space heating, but for domestic hot water, this seems to be less, around 20%. Based on this, it is important that we address what is causing this difference or gap, as there's a risk that systems in Ireland may underperform. On the next slide, on the left, you'll see a list of the reasons why these systems tend to underperform, and some of them are due to the calculation methodology itself, or not representing certain phenomena such as defrost or humidity correctly. It may also be down to separating heating and hot water in standards, where there might be a lot of examples in use where heating and hot water are occurring simultaneously. Outside of this, also there is a need identified from literature to train installers and users, and more importantly, there's a need to measure going forward. So, to summarize what we're doing in the Design Friday project, we're measuring the performance of 5 air source heat pumps. We're calibrating a high resolution model to extrapolate that to also look at the different scenarios that affect these, and we're also gathering the opinions and perspectives from industry professionals in the heat pump area. So, with that, I would like to thank you all. On the next slide, I'd like to thank you all for listening, and we're currently our air source heat pump survey. You can find it by scanning this QR code on the bottom right hand corner, if for those of you who want to find it. Thank you very much.
Thanks very much, Adam. So we're on to our last presentation, and then we'll move over to questions and answers. So just keep putting your questions onto slido.com using MaREI as the hashtag, and it's great. There's about 80 questions there coming through. So next presenter is Johanna. So Johanna is an architect and a planner. She's working with the Irish Green Building Council. She's also collaborating very closely with some of us in MaREI, and she's going to talk about a one-stop shops for deep retrofitting homes in Ireland. So over to you, Johanna.
Thank you, Jamie. Next slide, please. Okay, so we're working on a one-stop shop energy retrofit platform with NUI Galway and 7 European partners. It's a EU H2020 project, and it's called Turnkey Retrofit. The purpose of it is to bring a high-quality retrofit and pleasant journey for the house owner. Next, please. So you already know about the National Climate Action Plan 2019. Action 47 is establish a one-stop shop model for energy efficiency upgrade, and Turnkey Retrofit aligns with this. Next, please. Currently, there are many types of one-stop shops, end-to-end management for energy retrofit in Ireland, and they fall into these sorts of categories. One is the community energy agencies. The other one is main contractors, a professional service and main contractor, partnerships between energy company and financial institution, and utility companies. Next, please. So this is slide just shows what one homeowner seeking out a contractor to retrofit their home experience. So the comments range from a heat pump is a bad idea to, they only do certain types of retrofitting, like, components. So like external wall insulation or PV. Next slide, please. At the beginning of this project, we did an existing customer journey, a generic one. So the customer thinks about improving their home. They wonder where to start. They might get bad advice directly from unqualified contractors. Then when they want to apply for a grant, the extra paperwork, the contractor adds a premium to that. They have to find finance separately. And if they get the finance, they naturally think of what's the cheapest way to do it. They might get an unqualified contractor, which then results in lock-in effects, or else more subcontractors are needed to complete the job. And then the retrofit is not up to standard. The works cannot be certified. There's no warranty. And then that customer disseminates that bad experience to other people. Next slide, please. So we're just imagining what if there was one platform where you could get peer-to-peer reviews, get your your questions answered. You could find an estimate. You could find out what the benefits are. You could get a loan offer. You could book a professional, impartial advisor visit. You could find out what grants and energy credits you could save, and your renovation works could even be monitored, and you could get a warranty at the end of it. Next slide, please. So I'm going to just talk about now the Hero platform, which is live. So if you go to hero.fr, it's just gone live, and it's what we're adapting. We're adapting this one-stop shop in the turnkey retrofit project. Next slide, please. So Hero has features such as, you can get an energy assessment, you can find an estimate, you can find out financing, and you can also find a professional. But professional in France means a registered contractor. Next slide, please. In addition to, we're also working on a feature called the punch diagnosis, which is being developed at the moment. So this is a very rough diagram about it. So questions are based on how you feel in your home, and through a series of questions, a diagnosis is made about what measures you should take. Next slide, please. And on the left, down on the left here, you can see it shows you your improvement potential. Next slide, please. So there's also a feature called the Smart Diagnosis, which is on the existing Hero platform now, where you'll be given a rating out of 10. And here in the example, it shows you a rating of 4 out of 10. Next slide. The Smart Diagnosis also shows you the savings you gain per annum, depending on the estimated investment and measures you take. So it's graded and it's scaled in 3 degrees: initial, intermediate, and complete. Meaning, like, the more you spend, the more you save. Okay, next slide, please. So I'm just going to say now about what we're developing in the Irish prototype. Next slide, please. So we've had workshops and many face-to-face meetings with SEAI, some registered contractors, city councils, government departments, energy agencies, utility companies, and also banks. Next slide, please. So these are the actors who will be part of it. And basically, the customer really wants a clear process. The financial institution wants a safety net. The qualified professional is there to do the roadmap and strategy to prevent lock-in. And the qualified main contractor wants a certainty of a pipeline of work. Next slide, please. So the difference, what we're adding on our platform to the French one is that we really want to put something where someone gets a loan offer, they get impartial advice, that's very important, and some form of monitoring of work and warranty. Next slide, please. So this is where we are with our one-stop shop platform. It's a flow diagram so far. So we have all the things on the French one on the top one, plus the loan offer. And I think the difference in ours is this building renovation passport, which we would like to add, and it's what it can offer in aggregation. Next slide, please. So once a person fills in what they want to do, it goes into a building renovation passport, like a logbook, and from that information we can aggregate it, and from that aggregation we can probably put it into project bundles for contractors to bid, increasing the economies of scale for such a thing. Okay, next slide. Oh, so that's the end. So that's a turnkey retrofit project. It's to guide your retrofit journey. And the next slide, I would just like to invite you. Tomorrow, we're going to have a presentation about the French prototype. It's at 10 a.m. If you'd like to attend, could you please email me? And also, if you have any feedback or you think of anything you could help us with the OSS to bring it to a minimum viable product, I'd really like to hear from you. Thank you.
Fantastic, Johanna, that's brilliant. So that's the end of our presentations there. So we move into the questions and answers session. So just to pass the apologies from Brian Norton. So Professor Brian Norton from TU Dublin was due to moderate this session, but due to technical difficulties, he he hasn't been able to do so. So I'll moderate the questions. We've got about 10 minutes. So there's 88 questions in there. So we'll answer what we can in this session, and then the other questions we'll deal with and answer them afterwards and make it available to everybody. And we said as well that we'll also make the recording from today available as well after the event. So I'm trying to control Slido here at the same time. So the top one there, excellent presentation, Gary. So my mother was right. Put on a jumper if you're cold. So Conal, all our mothers are right. So we just should listen to our mothers. I think that's the easy answer to that one. So I'll go through, I suppose, some of the ones I've wrote down here. So Gary, the first one, I'll try and do an order of presentations. So there's a question there. A couple of questions I'll put towards you. So the first one being, how would your approach be scaled up? And then who should introduce these new societal and behavioural elements into retrofit programs? And linked to that, then maybe should it be to access grants? So some of this be incorporated in there to be able to access grants. So it's kind of three questions rolled together. So about scaling up, who should introduce the societal and behavioural elements into retrofit program, and should we link them to the grants?
Okay, thanks everybody for the questions. I think, well, approach to scale up, well, the grants suggestion is one approach that could be used to scale up, but I think what's important is to recognize that we cannot continue on with the lifestyles that we have. We cannot, the average CO2 per Irish citizen is 13 tons a year or something. If we want a 1.5 degree lifestyle, we should have 2.3 tons by 2030. So we're looking at a 80% reduction in our emissions per capita. That's if we're interested in social justice issues where we feel that everybody else has as much right to emit carbon as we have. So I think what we really need is a national, if not international, conversation about standards of living, what's acceptable, what's not, who should have be able to, can we go on and consume as much as we want, and the only limitation being whether we can afford it or not? Is that morally and ethically acceptable, etc.? Is it desirable to have ever increasing size of houses, to have bigger cars, to have bigger fridges, to have more, bigger, better of everything? And what's driving this kind of obsession with material elements, which we know from a lot of research that don't make us happy? What makes us happy is having strong relationships, good family ties and social supports, etc. So at the same time, we also have to have minimum standards as well. So it's good to recognize that some people do not consume enough, and they need to consume more because they live in energy poverty, etc. So there is a balance between minimum and maximum that we should try to live in. So I think if we want to scale this up, then everybody needs to be involved in the conversation. And so there's a role definitely for the media, instead of just pushing kind of this aspirational lifestyle, etc., that doesn't really exist. There's a role for businesses to produce more durable goods. There's a role for governments to bring in legislation and regulations around these areas. So I think everybody needs to be involved. In terms of using retrofitting as a particular example of a rupture in a lifestyle that can introduce introduce more sustainable behaviours, tying it to grants is a good idea. I think there needs to be more social science research involved, and it's not just, all the funding goes to technical research. Funding for SSH tends to go to behavioral economics, which I've shown might not be the best approach. So we need to try out new ways of experimenting, etc.
Thanks, Gary. Okay, that's great.
That's probably my time up.
Yeah, okay, that's great. So I'll just pose the next question. So I see the question there from Paul Kenny. Well, it's not a question, actually, it's a statement from Paul. Mechanical ventilation system should be mandatory for all retrofits from a health point of view. That's relative humidity, radon, other pollutants, COVID impact, and so on. So I think that's that's a statement that I would agree with. I don't know if there's others who want to comment on it. You can pick it up later on when I pose some other questions to you. So I'll go on to Paul next. So Paul, there's a few questions linked to your work. So Connor has asked, have you looked at any ways of adjusting the values from DEEP, which is the methodology for getting our building energy ratings? So is there any ways of adjusting those values within DEEP so they can better reflect the actual energy demand? And then a couple of other follow-on questions then. Could you see a post-occupancy BER being introduced in the future to validate the preliminary BER as a measure to address the gap? So I'll put those two to you, Paul.
Thanks, Jamie. I'll answer Connor's first. For my research, I adjusted the solar radiation values and the external temperature values to match up with the housing estate, just to make my analysis a bit more accurate. Then regarding adjusting all the other variables, no, I didn't, but it's definitely something to look into in the future to see how much of an impact or how much the change is required for the building to become, or the model to become more accurate. And then the second question, what was the second question, Jamie?
Sorry, the second question was, could you see a post-occupancy BER being introduced in future to validate the preliminary BER as a measure to address the gaps?
I think it's a possibility. I think other countries do that for their energy performance certificates. I suppose it's all about the resources required to introduce that kind of measure within Ireland, and I don't know if they are available or not. But I think it's definitely something worthwhile doing for us to get more accurate information.
Okay, thanks, Paul. So sorry, I'm just whizzing through the questions. As I said, there's we're going to answer all of these questions afterwards. So I'm just trying to get a couple of questions to everyone. So we move over to Martha next. So Martha, there's a few questions here for you. So one is, could positive ventilation reduce radon concentration? And there's a few in there about the impact of the ground floor. So the ground floor construction on the radon concentration level, and then potential, I suppose, issues then by introducing barriers and the impact that has on the high growth thermal stress, in particular, like on historic solid walls and so on in there. So linking to the first part, if we have a positive ventilation system in the building, and we have a sump underneath the floor, then if we have a low radon area, could that be enough without having to put in a barrier in there?
Okay, so yeah, looking at the regarding positive pressurization, I think you mentioned this technique is effective, but normally as I mentioned in the presentation, soil depressurization is the most common. Also, it's the effectiveness of the soil depressurization. It's reported as higher than the membranes. So, as you mentioned, sometimes including the membranes can have other effects. And also, in terms of radon barriers, like normally the damp-proof membranes are sufficient for radon. There are a lot of studies on that, but the installation of these barriers regarding radon is not always as effective as it's when you test the materials in the lab. So normally the most effective method is the soil depressurization. And regarding the types of the concretes and the foundations of the houses, on the review of the publications I commented earlier on, some of them did listed, like they were studying sample size of, like the different studies have different sample size, and some of them did relate the type of construction, like the slab on grade or suspended floor to the indoor levels. But I was just, like, in the presentation, I only highlighted like the biggest picture and the outcomes. But if you look into the different papers, you could find more information about that.
Okay, thanks, Martha. So yeah, so I suppose you're highlighting there that a sump on its own is not effective, I suppose, unless you have an extraction system working. So either a passive system or else put a mechanical system like a fan in underneath there.
Yeah.
Yeah, great. Okay, so we'll move on to Noel. So Noel, I have a question for you. Here we're asked, are the models automated, and how challenging will it be for people to operate the technology? I think this has come up like a few times in different streams and different questions throughout the morning. So in terms of the automation of your system, but I suppose more importantly, how challenging will it be for people to operate the technology?
Well, it's a relatively straightforward technology. It's nothing new. It's no more complicated than operating the existing heating system of an existing building. The kind of application will probably be more for apartments, buildings, rather than maybe say domestic houses or large scale, maybe offices or something like that. But it could be integrated into the existing control system. In terms of controls, it's not that much more complicated, really. And sorry, there was a second question there. Did you say there was a second question?
So Fergus is asking, is it similar to what they did in Elm Park?
I'm not hugely familiar with Elm Park, to be honest with you, but I know there is quite a number of double skin facades and ventilated facades around office blocks currently. Most of them are how this differs is it's the use of switchable glazing. So we're going to use the facade to collect energy, not just transmit energy when it's needed. This is going to be used to collect and store energy and release that energy when it's actually required. Whereas double ventilated facades are basically used to kind of transmit energy or control energy. This is controlling and storing energy. That's the difference.
Okay, very good. Okay, so just I'm conscious of time here. We're just gone over 12 o'clock, so we'll move on to Adam. So Adam, there's a few different questions on your side. So are there any studies that show how solar thermal and PV can enhance the performance of heat pumps, especially for hot water in the summer? And do you notice any widening or shortening between the actual and rated performance gaps during the shoulder seasons?
Thank you for those questions. I suppose on the solar thermal and PV specifically, I can't really comment on that. I don't know that to hand. And the second question being about, can you repeat that question if you don't mind? The actual versus...
Yeah, sorry. Do you notice any widening or shortening between the actual and rated performance gaps during the shoulder seasons?
Yes, so we're monitoring at the moment. We're monitoring about 5 heat pumps. 1 is commercial. We've got 4 domestic. We've been monitoring them. We're now obviously we're just coming over the shoulder season into the summer, so I don't have that information to hand, but that is something that we will look into.
Okay, thanks, Adam. So just on to the last presenter then, Johanna. So there's a few here for you, Johanna. So one is linked to the Department of Community Climate Action and Energy. Hopefully I've got that right. Have a retrofit task force to develop a new model to support the building retrofit ambitions. Is the approach from the turnkey retrofit proposal feeding into the process? And a follow-on question then, who will host the tool is the follow-on question.
Okay, well, we are talking with the department, with DK, so it's not really at the stage where we know that much yet. So that's all I can say about that. But we are speaking with them and we are communicating with them and what's happening. And who will host, that's also something we're deciding now. There are a number of interested parties, and then because it's still at the developing stage, we have to decide what type of business model we're going to use and who's going to be part of it. That's all I can say. Thank you.
Okay, thanks, Johanna. So I'm just going to wrap up the questions. I see one here at the very top that's got a lot of likes here. We're customers who have recently purchased an F-rating 60s built in Dublin. What advice can the panel give for our renovation and retrofit? I suppose my number one advice is to employ a qualified consultant that has experience in retrofitting homes, and that is a key. I think that to get those professionals that have the experience and the training and qualifications to do the work in there. Okay, so if that's so, that's we'll close the question session there. I think just I know we're gone about 3 or 4 minutes over time, so just trying to be conscious, trying to keep it within the 2 hours or so. So I just was to close up and to say a few final words. So thank you everyone for joining us, and hope you find it interesting. I see some positive comments coming back on Slido already on this. We had over 500 people registered, and I think at any one time we had over 250 people here this morning. As I said, the presentations this morning, or the recording, will be made available through the MaREI website afterwards, and people will get an email on that. Hopefully people found it worthwhile joining and taking the 2 hours to join us, listening to our researchers from the MaREI Centre, sharing their insights, I suppose, into the challenges and opportunities that's faced. It is a big challenge, but also a huge opportunity for the country, aiming to get 500,000 homes retrofitted by 2030. It's something we need to do, but then that's huge, major economic and employment opportunity. It may mean that if we can get it right, that we have less people having to travel from the north, midwest, west, south, southeast, and so on of the country into Dublin. Construction workers in there every day. Maybe if we can scatter them around the country and to concentrate on retrofitting homes throughout the country, it's local employment and local benefits there as well, rather than a capital-centric approach to things. So it's crucial, I suppose. You heard there from many of the presenters that there's multiple benefits of retrofitting beyond just energy efficiency, taking into account, I suppose, the 3 pillars of sustainability, economic, social, and environmental context. And it's crucial that those wider benefits are understood, that they're quantified and demonstrated to stakeholders to drive retrofit uptake, investment, and policy design. And I suppose that's what our researchers are good at. They're good at and that type of stuff. So we've seen some important learnings presented this morning from retrofit works that have been already undertaken, such as through the Super Homes scheme run by Tipperary Energy Agency. We can also see the feedback from yourselves, from the initial questions, and a lot of thing there in terms of barriers and what the government need to do in terms of supports for funding, finance, and grants to help achieve the 50,000 retrofit homes. As I said, we had about over 90 questions there. We couldn't address them all, but we will follow up with everyone here on the panel today has agreed to follow up and answer those questions afterwards. We'll put them into one document. And as I said, the session has been recorded and be saved onto the MaREI website. Just to give a thank you, I suppose, a few thanks yous at the end to our fantastic 12 panelists, to Josephine Maguire from the Sustainable Energy Authority of Ireland for moderating the first session, doing a very good job, and the biggest thanks has to go to both Tara and Aoife, who are in the background there. You didn't see them popping up on the screen at all, but the whole day today went very efficiently and smoothly thanks to all their hard work. I mean, there's a lot of work and effort goes in there into it, so a huge thank you to those. And with that, I'd like to close the session, so thank you.